on the campus this morning was an average of 30 miles per hour, then what's the average velocity you think I'm going to have going home? I think it's going to be negative 30 miles per hour. Do you see the difference between velocity and speed? I think velocity is an example of a vector. It's got both the magnitude and direction, the negative sign meaning direction in that case, as opposed to a number or a scalar, which only has magnitude. There's a difference. Now I've got to confess, I had a nifty way to represent this in our nifty little Cartesian coordinate system. And if I went ahead and plotted a point, namely 2, 1, excuse me, I misspoke, didn't I? Sorry. 2, in this case, 3. It's just a point. It's a location, two-dimensional space. Oh, by the way, it's not a vector. However, if I drew an arrow emanating from the origin and terminating at the point 2, 3, I might refer to it as a vector. I gotta confess, you guys, my notation probably gonna have to change. I guess I shouldn't use open parenthesis 2, 3, close parenthesis. You might confuse that with an ordered pair. So if you guys don't mind, I'll change my notation to 2, 3. I'll just use different notation. Well, I think I just misspoke. I'll use different notation this semester. Next semester, I'll prove to you there's no difference. Do the same. I think for any standard linear algebra course, wherever you take it across the entire country of the United States, the very last sentence your linear algebra professor will say is that it doesn't make any difference what notation you use, the underlying mathematics is the same. But to be official, because I'm speaking mostly to those of you in this room who are engineers, I will change my notation to what you see in blue to represent a vector as opposed to not. Now, I gotta confess, I think to locate the terminal point of this vector, located the black point 2, 3, what I really do is what I did back in Math D, namely stand at the origin, walk 2 units to the right, 3 units up. It's just that I might refer to this particular vector you see drawn in blue as a vector in standard position because the initial point is at the origin. It doesn't have to be. I'll change that in a few minutes. Before I do, can I change my notation? Because I know what you just said. To locate this terminal point, I'll walk right 2 units and up 3 units. Sometimes I have a tendency to just simply write this as a 2 plus 3. Oh, actually I can't, because it's just 5, isn't it? I made a mistake. Let me change my notation a little bit. I meant to say, I'm going to walk 2 units in the horizontal direction. I have a tendency to refer to this 2I bar plus 3J bar, where I bar and J bar are 2 vectors that are very special. They're called unit vectors. Specifically, I bar is simply the vector walking 1 unit to the right, 0 units vertically. And J bar is just the opposite. I'll even say, in English, these are my standard unit vectors in 2-dimensional space. What it'll look like in 3 space, if you guys don't mind, pray tomorrow before I discuss that. For now, I gotta confess. If I went in here and drew myself a nifty little triangle, in such a way that it's a special one, it's a right triangle, and I think of this angle right here as theta, is an angle in standard position whose terminal side is what you see in blue, that blue vector. Then would you guys not agree that when it comes to this length right here, that horizontal dimension, can't I think of that as nothing more than, I don't know, anybody? The cosine of the angle theta times the magnitude of the vector. Oh, I better multiply it by I bar. Plus, yeah, I think so. I think, actually, did I say 2? You guys, I'm serious. I just made a mistake. I don't mean to say that the coefficient's 2. I'm in error. What is that coefficient on the front? Yeah, I think it's technically speaking the magnitude of the vector, but the magnitude of the vector is the square root of.
Oh, it's squared plus root squared.
So in this case, square root of 13, because I'm just looking at the length of the hypotenuse of a right triangle. So my mistake, I put a 2, I meant to put root 13. And likewise, using my right triangle definitions of trigonometry, I think the second component is nothing more than the magnitude times the sine of my angle, if you can read it, jeepers. I said the magnitude times the sine of the angle theta times my J bar. You guys on the board, I've got 1, 2, 3 completely different ways of representing my vector. notation, but it all identifies the same darn vector. You guys, so far, is this an absolutely boring piece of cake? I'm just stealing from your past trigonometry. Nothing more. However, if I have in the Cartesian coordinate system x-axis, y-axis, I don't know, you guys, I'm making up a point out of thin air. How about x1 comma y1? By the way, it's a point, it's not a vector. If I have another point, say, how about x sub 2 comma y sub 2? I think I can create a vector emanating from the initial point x1, y1, terminating at point x2, y2. It's just that when it comes to this vector, I can quantify it using my first notation of blue. Would you guys not agree this vector could be represented as a vector whose first component is just a difference in these two x coordinates, whose second component is just a difference in those y coordinates? I'll give it a name. I'll call it, how about the letter V for vector? Actually, you know what? I can't call it V because you might mistake my letter V as a variable, and it's not. I meant it to be a vector, which means it's got both direction and magnitude. So let me fix my clumsy mistake. If I'm a textbook, peace out, okay, I'll do the bold print. I'm not a textbook. I'm at the ink board. I can't do that. So I have a tendency just to put a bar over it. I don't know where you guys are coming from. When you were raised trigonometrically speaking, you might have done something a little bit different. Maybe you had the caret key. Maybe you had an arrow, or maybe you even had a half an arrow pointing to the right. You guys don't change your notation if you're used to some other notation. I understand completely what you're saying, what you're writing. Personally, in class, if you don't mind, not to change your ways, I have a tendency to put a bar over that letter V, so that you understand that there is a vector. If I were to dive in and give you two vectors, ay, ay, ay. These are only erases by definition. If I handed you guys two vectors, how about this one and this one? Can somebody tell me in English, in words, how the heck I would have these two vectors?
Set one with its origin at the ending point of another one, then draw a line from the starting point of the first to the ending point of the second.
Perfectly good. I agree completely. Take the initial point of one, I don't care which. Place at the terminal point of the other. And now what I'm going to do with my green pen is I'm going to go from the initial point of the first to the terminal point of the second, and this is what I'm going to refer to as V bar plus woo woo woo. I said V bar plus W bar. Sometimes I use a funky word for that. I refer to it as resultant, or shall I say, resultant vector. It just simply means the sum of those two vectors. Graphically speaking, what I'm really doing is using something a lot of people would refer to as a parallelogram method of adding. I say parallelogram because, technically speaking, with my blue pen, I could have started off with W and then added to it V bar. And so does everybody agree with my picture? I'll wait till you get caught up. You guys are real harmony.
I think you switched to the W and the V.
You say you made a mistake.
In the blue. You just started with A and W.
I think I did. And I think this is important. So you guys check this out. I think I mislabeled everything. Technically speaking, this vector in blue down here really is a duplication of W bar. This one's V bar. But my point is this: is W bar plus V bar the same thing as what you see in green?
Yes.
Okay, what this really says then is the following. It basically suggests that when you add V bar to W bar, order is completely unimportant. We sometimes refer to that as the commuted property for addition with vectors. May not be that big a deal, may not be that ground shattering. It is. Because I think a lot of times in mathematics, when we add things, commutativity does not necessarily hold. Well, I shouldn't say add things, I misspoke. I meant to say, a lot of times when I combine two things in mathematics, commutativity does not necessarily hold. It certainly doesn't hold with subtraction in the real number system, nor division. Is multiplication commutative? Yes. Oh, two mathematical entities, what were they?
Was it with imaginary numbers?
Not imaginary numbers, but
Negative numbers? No.
it still works with negative quantities. Oh, you guys, give me a location, two things. Oh, you know what, that's a good point. True, when it comes to cross product, connectivity is not whole. Whatever cross product is, if you don't remember, don't worry about it. I'll remind you this semester.
Matrices?
Matrices is a perfect example. Multiplication does not fit. Do you think this is going to be true? If I take a vector u bar, v bar, w bar, if I add the first two together first and then add the third one, do you think that's going to be the same as adding v bar with w bar? And then adding to that result u bar?
Yes.
Yeah, I think it's going to hold. I think intuitively it does hold. As a matter of fact, I can prove to you it holds without any writing. Just by definition, how we add vectors, I think it's just adding components. But these components are real numbers, and since associativity holds for the addition of real numbers, it's certainly going to hold with the addition of vectors. Here too, associative property. If you guys are just taking Math 32 this semester, don't worry about it. If you're taking 33 this semester as well, it's a big deal. I'm going to have a list of items, 10 I might call them axioms and postulates, describing what a vector space is, and that's one of them, as well as commutativity. For those taking Math 33, you know what I'm referring to. For those who are not taking 33 or haven't taken 33, you'll know what I'm talking about in the future. I missed something, you guys. Help me with this. Is V bar and 3V bar the same thing? No, I think 3V bar is V bar with the direction changed to what? Yeah, it changes nothing. It doesn't change the direction. The only thing that changes is the magnitude is going to be 3 times what the magnitude of V bar is. Do you guys agree? If in the Cartesian coordinate plane, x-axis, y-axis, I've got a vector in standard position whose components are A and B. I'll call it V bar. Somebody tell me the length of that vector. Perfectly put. I think it's just a square root of a squared plus b squared, just using a darn Pythagorean theorem. So if you guys don't mind, I'll introduce some notation. I'll refer to this as V bar. Is that okay? Oh, you're right. I made another mistake. I guess using notation, V bar is referring to a vector which has both magnitude and direction. And to be honest with you, square root of a squared plus b squared is just a number. So I made a mistake. How will I change it? I don't know. I mean, I got so many different ways of writing this, you guys. I have a tendency just to put what might look like absolute value bars around the V bar. There really aren't absolute value bars because V bar is not a number. But I use that notation to represent the magnitude of that vector. Some of you might be raised differently. Some of you might say, oh, it's double bars. That's fine. Again, you guys use whatever notation you're comfortable with. In class, I tend to use single bars to represent the magnitude of my vector V bar. Oh, by the way, I didn't say this, but because I'm here, can somebody tell me something about the angle of theta? Can somebody just panic and say something about theta in terms of A and B?
We can calculate it from A and B.
And we can, but how?
I can't remember the name of the theorem.
I like it. I'm a little nervous about the inverse part. If you don't mind, I'll just cheat. I'll just say theta is an angle whose tangent is the ratio B to A. That's opposite over adjacent. I like saying it this way instead because when I talk about inverse tangent of some angle, excuse me, this is over. When I refer to the inverse tangent of some number of angle, I'm really referring to an angle between negative pi halves and positive pi halves, and this gets me out of that restriction for the inverse tangent function. So I'll say it this way instead. So if I give you guys a vector in V bar like this, I want a yes or no answer. With the notation I'm using on the board, is length of this vector V bar going to be positive? Well, is it positive one, I should say?
Depending on what A and B are.
Yeah, it depends on what A and B are. I think in general, here's the magnitude of my vector V bar. It's not necessarily equal to 1, but sometimes in mathematics I want to force the issue. I want to force the magnitude of my vector V1, but going in the same direction as V bar. And if I want to create a whole new vector out of thin air in the same direction as V bar, but whose magnitude is 1, I might refer to it as a unit vector going the same direction as V bar. And I think the corresponding unit vector going the same direction as V bar, but whose magnitude is 1, is going to be nothing more than V bar, but divided by the magnitude of V bar itself. I think this creates a whole new vector going in the same direction as V bar, but whose magnitude is positive. You guys agree? What can you guys say about the relationship between these two vectors? By the way, they're both these.
They're gonna be exact.
Exact,
Direction.
opposite direction, same magnitude, but in the opposite direction. So, my cat Archimedes likes to sit on a shelf that I created. I suspended from my ceiling. But I suspended this from a different or multi-level ceiling. And it's the case that one rope hangs, excuse me, not hangs, but connects one end of this platform to the ceiling at an angle that's, I'm making these numbers up out of thin air, you guys, whose measures 58 degrees. But with the other part of the ceiling, this angle measures 50 degrees. And I think, for my cat Archimedes, it creates two tension vectors, creates tension on these particular ropes. And I do think they're vectors because they have a specific direction. I'll call one T1 bar, and I'll call one T2 bar. And if my cat Archimedes weighs 10 pounds, do you think there's enough information I just slap on the board to find those two tension vectors, T1 bar and T2 bar? Yeah, I think there is enough information. How can I find these vectors, T1 bar and T2 bar? So,
Well, we're assuming that the platform's at rest, right?
thank you. I have to confess, I'm assuming that is at rest. Yes.
Okay, then we can break up what will be the two T1 and T2 vectors into their components. We assume that the two vertical vectors of T1 and T2 together have to add up to be equal to the weight of the cat. And because it has to be at rest, the two horizontal components of the T1 and T2 vectors have to counteract it.
See, I kind of like the way you said that, which I don't think is necessarily the way your author says it, but I like it. Can I just change the words a little bit? You said T1 bar and T2 bar add up to the weight vector. You really meant they add up to the opposite of the
I
weight.
might have left out the vertical voice. If you notice, I actually said horizontal when they counteracted.
See, I like that. I like the way he said it. He's saying, when I take T1 bar and green, add to a T2 bar and green, I should come up with the opposite of the purple vector. By the way, if you do them in Inkboard, I know they don't match up. I do a lousy job drawing. But technically speaking, I would say the system is in equilibrium when green plus green equals the opposite of purple. Your author doesn't say this. Your author says, if the system's in equilibrium, nothing's moving, then it really is a case that the sum of the three vectors you see as is in green and purple is equal to 0. Well, I should say, is equal to 0. Vector, not the 0 as a number. So I don't care which way you guys look at it. Doesn't make any difference to me. So, because I'm in front of class, do you guys think I can do this the way your author does it? Just so when you go home, you look at my notes, it's consistent with what you see in the text. By the way, I'm going to violate that a lot this semester. There's a lot of things in here I really don't like from Apple YouTube. So if you guys don't mind, can I look at the purple thing? Can I think of this as W bar? W bar for weight. So you guys help me with this. When it comes to W bar, as a vector, what are its components? 0,
10. Negative 10.
Negative 10. And I think my T1 bar, I'm just looking to make sure I'm using the right notation. T1 bar can be interpreted as I like that, but you really meant T1 bar's magnitude times the cosine of, I can't see it. I can't hear you.
50 degrees.
I still can't hear you.
50 degrees.
One more time? Yeah, what is that angle in standard deviation?
Oh, it's 360 minus 50, which is 110, no, 310.
You know, I could do,
130.
you said 310?
130.
I can do this by changing direction, but how about this? How about you saying, it's 1/4, half the revolution is 180, backed up by 50, which is 130. Comma, hold it, you can't read that. Comma. This is painful. Magnitude T1 bar.
Assign that on 130 up.
Got it, I agree. Likewise, now that you're on a roll, I think T2 bar can be interpreted as, oh, you guys.
Magnitude T2 times
The old one. It's too early. It's your mistake.
122.
Sit again.
122.
Little louder.
122.
Hold on.
It's 58.
Where'd you get 58?
Are we on T2?
180 plus 58 is.
I'll wait.
I'm doing this on my calculator.
You guys, what's this angle? I heard the 58. I agree with the 58, but why?
Opposite interior angle to
Thank
the
you.
upper
I think, I'm sloppy, I know, but these are technically speaking two parallel lines. I got a transversal for those two parallel lines. And you learned back in high school geometry that opposite interior angles to a transversal for two parallel lines are going to be
Equal.
okay. Well, the angles are congruent. You mean the measures are equal. I agree. Bless you. Quite all right. So I'll put it in. Did I say 58? I lost my number. Comma, the magnitude of T2 bar times the sine of the same darn angle. Oh shoot, I haven't answered the question. My question was, can we find those vectors T1 bar and T2 bar? Piece of cake. Because I think it is the case that some of these three vectors is equal to zero vector. Sorry, I didn't mention zero vector, did I? Shoot. I better backtrack. Zero bar, the zero vector, is nothing more than a vector whose magnitude is zero, and I don't know what you want to say about finishing my sentence, about direction. You might say it's got in the direction of everywhere. Technically speaking, in mathematics, we say that it has no direction because it's not playing in no given direction. And that being the case, everybody, I get to play. I get to play because now I can just simply rewrite the sentence, but I'll rewrite it in terms of vector notation. I think T1 bar plus T2 bar plus W bar being equal to 0 bar means nothing more. Then, T1 bar, shoot, you guys can do a better job of this. Ooh, that's nice. So T1 bar's magnitude times the cosine of, I forget, is it 130? Plus T2 bar's magnitude times the cosine of 58 degrees. Comma. T1 bar's magnitude, everybody look. I forgot my subscript. I think I said it, I just didn't write it. That was T1 bar's magnitude. Comma, T1 bar's magnitude times the sine of the 130-degree angle plus T2 bar's magnitude times the sine of the 58-degree angle. Is this going to be equal to 0, 0? Or did I miss something? Oh yeah, I forgot the second component of the third vector W bar, which by the way is negative 10. I'll put it in. So, question. Is this a math D question? Thank you. So I think it is a math D question because for two vectors to be equal to each other, their corresponding components have to be equal to each other. So I think what this one single equation really tells me is that I've got a system of two equations and two unknowns, namely T1 bar's magnitude times the cosine of my 130 degrees plus T2 bar's magnitude times the cosine of the 58-degree angle has got to be equal to the first component of this vector. And likewise, the second component on the left-hand side, that would be T1 bar's magnitude times the sine of the 130-degree angle, which I can't write. plus T2 bars magnitude times the sine of the smaller angle, minus my 10 is equal to 0. You guys, I'm running out of room on the inkboard. Can I cheat? I'll add 10 to those signs. I got two equations with two unknowns. I can solve that system piece of cake. Look at the first equation. If I were to isolate T1 bar's magnitude, doesn't it tell me T1 bar's magnitude is, yikes, I don't know. Is that negative T2 bar's magnitude times the cosine of the smaller angle all over the cosine of the larger angle? You guys, I'm serious. If you don't know me, please just make sure my arithmetic's okay. Oh shoot, why am I doing this? I said, oh shoot, why am I doing this? So I can substitute back into the second equation, P sub k. Now with that second equation, I suppose it tells me T1 bar's magnitude times the sine of 130 degrees. Which, by the way, this is garbage, times 130 degrees. Which, by the way, is negative cosine of 58 degrees times the sine of 130 degrees, all over the cosine of 130 degrees, plus the sine of 58 degrees is equal to my 10. What's that?
Magnitude T2.
Oh, I forgot to put the magnitude of T2 bar. How many times? Twice. I'm too tired. I'm lazy. Do you guys mind if I only put it in once? Since both these terms have a factor of T2 bar's magnitude, I'll pull it out. Oh, shoot. That means life's an absolute piece of cake. Now, isolate T2 bar's magnitude. I'm here looking at the divide both sides by that coefficient. But I think in the end, it merely gives me, I have no idea what it gives me. Is that 10? You guys help me. You're making me do all the work. Is that the sine of 58 degrees cosine 130 minus cosine of 58? Sine of 130? Oh, I can't write the 130, sorry. I said 130 degrees. And by the way, this is degree symbol, not a power 2. You guys, so far so good. Is that okay?
Yeah, right.
You just tell me if it's not. And I'm pulling out my nifty little calculator. So you guys can watch me so we're on the same page. I maintain, oh, you guys can't see it, can you? Shoot, we're a little slow. All right, I'm back. Do we all have a table? Forget. Do we all have a table? Oh. Yes, we do, because technically speaking, you guys watch me. On my computer, if I access a virtual TI icon, I can pull it up. Now that we all have a table 3. Yeah, because technically speaking, you guys can go in the Math Center and you can go and pull the 83 just like I do with the virtual TI. You can even save copies of the image and put it on a piece of paper if I ask you to, in terms of turning in Word for quizzes, particular quizzes. If you want something like this at home on your computer, shoot. I came to class unprepared. I'm pretty sure you guys can access this at home if you ask permission from the Math Center. I'm pretty sure. Because I think we got a license for you guys to take this. But you have to ask the Math Center to be sure. Yes?
You could just download it off like Pirate Bay or something.
What's it called?
Pirate Bay.
I've never done that. I'm sorry. I'm just so honest. Eric, are you serious about me? Have you done that?
Of course. Like,
No, I meant specifically the virtual TI.
Oh, I've never tried it. I'm sure you could.
I'm sure
You've tried it.
Yeah, let me know if you guys can check it out. I should have said that. You're not supposed to let me know. Anyway, by plugging everything in, help me with this. 10 cosine of 130 divided by the sine. What's that from?
The cosine and the parentheses.
All right, technically speaking, since I'm the one who accessed the cosine function on my calculator, it automatically opened up a set of parentheses. I have no choice. I gotta come in, backtrack, and literally close the parentheses. I'll do just that. And I'm dividing by the sine of 58. Sine is, I forgot the angle was.
It was 58 degrees.
Well, I think it's irrelevant. Because I think since I'm dividing by a multi-term expression, what I have to do first is, I think it's parentheses. I'll go back. So technically speaking, I'm at the open by parentheses, and then the sign now becomes, it's a 58. Cosine is 130. You guys help me with this, is it minus the cosine of 58?
Yeah, minus cosine 58 times sine 130.
Sine 130. You guys ready? Everybody ready?
Yeah, Math 33 starts in like 10 minutes.
No, you're not ready because
We'll be standing in that class too.
I have no idea what the mode is. I gotta go back in. I do so low in mode. Yeah, just make sure that I'm in degree mode. Oh, look at that, I wasn't. So I'll put it in degree mode. Okay, now I'm happy. I'll come back to my home screen and I'll enter. Do you guys agree? Yes or no? Do you agree that I found my vector T1 bar? I'm sorry, I misspoke. Do you agree I found my vector T2 bar? Yeah, I don't think I have. I think what this number really represents is nothing more than the magnitude of T2 bar. So technically speaking, I think T1 bar is a vector, which is what I asked for. It is going to have components of
T2?
sorry, that was my mistake. My apologies. Oh, if I'm around, should I write that as 6.76? My apologies. Cosine was it 58 degrees? Yeah, for T2 bar. Comma. 6.76. Boy, I just can't write today. Jeepers. Times the sine of my 58 degree angle. Actually, you guys, I think I made another mistake. This is not a true statement. Technically speaking, this is merely an approximation of the vector T2 bar. Did you guys ready to finish? T1 bar, piece of cake. Take that approximation of my calculator, slam back in for here, and you can find the magnitude of T1 bar. Therefore, T1 bar itself is going to have two components just like these, by the magnitude of T1 bar finished. And the angle changes to 130 degrees. Do I understand? Guys, give me a little feedback with thumbs. Yes, sir.
So those numbers, the 6.76
Yes.
times cosine 58 and the one beneath it, that's the coordinate for the end of the vector? If you point
Yes.
it at the origin? So
Yes.
that's your x and y.
I like the way you said that. If my vector's in standard position, meaning the initial point of the origin, this would be the order pair of the terminal point of the vector. I agree completely.
So then you just do figure out the vector.
The magnitude, if you want to figure out the magnitude, you could use or how it's cheap and give up, technically speaking.
Okay, so that's.
But I promise you, if you do slam this and this into the Pythagorean theorem,
You get that number, okay.
you're good. You guys, give me some thumbs for a minute. It's first day class. Was this a piece of cake review?
Is there a review chapter on this in the book, or do we have to go back to?
But I've actually covered the first chapter first. So
Huh? Oh, okay.
this is the first chapter. I said chapter, and it's the first section.
Well, this is review from Trig, right? So.
Well,
kinda-
it may be a review, but it's actually technically an entire section, the first chapter. So
Okay.
the author covers it just like I did.
Okay.
I'm just simply indicating that this really should be reviewed. So you got